Today we're discussing geologic time. This refers both to the age of the Earth and the age of the universe, but it's also determined by dating techniques. And you'll see some terms in the lab that may be unfamiliar to you. For example, relative dating. This is one category of how we measure time. It doesn't require technology, it's very old, it's based on common sense, and in your lab you will learn about Steno's laws. This gentleman here realized that you could put layers of rock in a sequence and read those layers as if they were pages in a book. Today I will go through each of Steno's laws and some other aspects of relative dating. Okay, the first law, the law of superposition. Oldest rocks are on the bottom here. All this says is that if I see a layered stack of rocks, maybe I'm hiking in the Grand Canyon, it's reasonable to assume that layer A formed before layer B. Layer B formed before layer C. Just like if you stacked books on a table, the book on the bottom of the stack would have been placed there first. Now, I mentioned the Grand Canyon. According to this diagram and according to the law of superposition, the Supai group is older than the Hermit Shale. Another law is that nature puts things out in a horizontal layer. That means flat. And that's because when this rock type wasn't rock yet, it was just liquidy, mud, goopy stuff, gravity spread it out. Gravity would never make things form at a layer. If you had a stack of books on a table, they would stack neatly. They wouldn't magically poke one end up into the air. So if I see a stack of rocks that have been tilted, I can assume that something happened to push them up and that originally they were flat, as shown here. Cross-cutting relationships. This one sounds very fancy, but when you see the diagram, it'll be reasonably simple. All this means is that if I have a flat layer of rock and something slices across it, for example, a volcanic vein of rock or a fault, whatever disturbs the original feature must have come second. The feature was there before it got disturbed. Right here, this stack of rocks was intruded by a dike of crystalline rock, a vein of rock. So this dike A is younger than everything it cuts. Everything in these layers was here before this sliced across them. Now you may have noticed on the previous slide, I mentioned inclusions. Sometimes the principle or law of inclusions is included with the other relative dating ideas. Now, all this means is that if I find a fossil in a rock, the fossil might be the same age as the rock. It also might be older, but it's not younger. Nobody magically cut a hole in a rock and put a fossil in it. For example, if you look at your purse or backpack right now, you might have stuff in it that's brand new, but you might have stuff in it that's old, even older than the bag that contains it. So an inclusion can be older than the substance that's holding it. An unconformity is what happens when one of the layers of rock is missing. Now, rocks go missing all the time. They get destroyed by wind, by water, by time, by erosion. Sometimes humans go through with a bulldozer and remove stuff to build a road or a home or a hospital. And whenever we have missing information, a missing page from the book, we call it an unconformity. And in this diagram, I mentioned 4 types. That's a mistake. This is why I don't teach math. There are clearly only 3 categories, so let's go through. Angular unconformity. This is when I have tilted rocks. Sorry, let me go back for a moment. This is when I have tilted rocks underneath flat rocks. So that would look something like right here. I have some rocks that aren't flat and then flat rocks on top of them. So the boundary between these two chunks and collections of rock is the unconformity. It represents time, missing information, what have you. A disconformity is a little trickier. This is when I have flat layers under flat layers, and unless I told you a layer was missing, you wouldn't know. So I would never trick you on a test. I would point out that the green layer right here under the purple is later missing. By the way, we don't know why it's missing. We just know that we can observe a disconformity. A nonconformity. Now, this involves two rock types, and I know we haven't talked about rock types yet, but there are rocks called sedimentary rock that are made out of old sediment. Sediment is a fancy way of saying dirt. So if I have loose mud, loose dirt, loose pebbles, and over time those become a rock, that is a sedimentary rock. There are other types of rocks. If you've been to a volcano and seen lava, that would be an igneous rock. Ig means fire. There are rocks made out of beautiful crystals that formed deep down in hotter portions of the Earth's crust. Those are metamorphic. And if I take a rock that's made out of crystals and was exposed to depth and heat, it can jump right through, it can shove its way through sedimentary rocks. And the relationship between the flat sedimentary rocks and this oddly shaped body of other type of rock is called a nonconformity. Now, what's the point of all this? The point of all this is solving puzzles. Nature presents us with clues, and using these Steno's laws, these reasoning techniques, we can then solve puzzles. So for example, what do you think is the oldest layer of rock in this picture? This is the surface, this is deep, it's cross section. Let me solve it for you. 1, 2, 3, 4, 5. These colorful tilted layers of rock formed. Originally they were horizontal, then they were tilted up. Now we don't know when this dike happened. This fault right here, this is younger than the dike. All we know about the dike is that it happened after the purple layer came down and before this event. This boundary right here, we're going to call an angular unconformity. And after all this stuff happened, then we get a bunch of flat layers. 1, 2. These get cut by the fault. Then time passes, 3, 4. You'll get to practice different little puzzles like this in this week's lab. Now there are several famous unconformities in the Grand Canyon. Let's see what we have here. Nonconformity at the very bottom. Some of you have hiked down here probably. It's a big job to get back out because you're very tired and you have to go uphill at the end of the day. Here's a nonconformity. Tilted layers, angular unconformity. Flat layers, disconformity, disconformity. Walking down to the bottom of the Grand Canyon is like walking through a geology textbook. Sometimes we use fossils as clues to decide that things are the same age. Maybe I visit the Grand Canyon and see some fossils, and later on I go to Zion National Park in Utah and see similar fossils. If the rocks contain the same things, I can start to figure out that they are correlating in age. Now, the geologic time scale was made using relative dating techniques. Before we discovered radioactivity, before we had any technology, just using common sense and observation and note taking and a good pair of hiking boots, people were able to make enough corresponding layers that they could actually create this beautiful time scale. And it goes all the way back to before we have life. And in this class, we'll talk a little bit in terms of time. For the next topic, we will discuss absolute dating. These PowerPoints are optional. They're meant to enhance your ability to complete the lab. You'll be reading about these topics as you do the lab. But if they help, watch the next one. Thank you.